Hello everyone. Today we'd like to cover reading assignment 19. The topic title is the beams under complex load. So until now we have discussed about the determinate and the indeterminate beams, and now we are talking about applied loading conditions. So we also learned about the boundary condition before. So think about the complex loading. So of course all the engineering methods are complex. If it is pretty much simpler, then it might be too easy to get a job, isn't it? So let's see the details. So complex load, how do you think about complex load? And here basically they want to introduce about the principle of the superposition. So basically think about the superposition. If this might be the good example, if you have the one and the other one, that should be two. So linearly we can add those two so that we could be able to get two. So that is several ways to apply principle of superposition, and until now we discussed about the beam methods. So they will provide, for example, the simply supported beam like this, and if let's say applied loading case is here, the point load as well as the distributed load at the same time, which means that we can split into two to solve these questions. So this is one beam, exactly same beam, and then we have P and Q. So in this case we will consider P only, and here we will consider Q, and then we will add up everything like the moment functions, you know what I'm saying, as well as the shear is also available. And once we get the moment function, this is exactly same as EI and the deflection 2 dot, meaning that we can get deflection functions one, just put it like 1 and 2. So the total will be W1x plus W2x, and M total, this is also same as M1x plus M2x, something like that. So this is the basic concept, and we'd like to apply this concept for the marine structures. So as you can see here, they are talking about let's see here. So marine structures, they discuss about the distribution pattern, and hydrostatic pressure is uniformly distributed over the horizontal members. In this case, for your better understanding, I'd like to write something here. So for example, we have the oil tanker, and you can see the shape of the midship sections, hopper, and the deck area, center line is here. So the hydraulic pressure will be applied here, isn't it? And the lateral pressure will be applied like this, you know what I'm saying. So the horizontal member is okay, and basically we can get it simply P, lateral pressure P is low GH. It is simple. But in the case of vertical members, for example, then we will bring this one to here. So this member will be subjected to, let me change the color again. It will be subjected to the lateral pressure. So the amount here, I will zoom in this one. So the applied lateral pressure, that will be like this. You know what I'm saying? So we will write this again. So if let's say if we have lateral pressure 1 and lateral pressure 2, so apply the loading condition is like this, then how we can solve these questions easily? So the way is, let's make it simple. So split into two, like this is area 1 and this is area 2, triangle shape. And then this is simply supported beam, and one is P1 is applied, and the other one is here. This part A2 is applied. So this will be P2 minus P1 1 and this is 0. So we can solve individually, and then later on we can add m1 plus m2. That should be same as m total. That's all. So make it simple. So let's see the details here. So hatch cover, all the details, you can read it. And the principle of superposition, just now I have introduced this one, right? M1, M2, M3, how many members, how many moment applied, it doesn't matter. So shear and moment applicable. At the same time, it could be applicable for the deflection as well. So let's see the example. It might be better for us to understand it better. So example number 1, they have applied the load here 10 kilonewton at 1 meter from point A and 20 kilonewton from point B to the left 1 meter. So basically let's split into two. So left hand side, this will be the new free body diagram for us. So 10 kilonewton is here, and in this case simply supported beam. Of course the total geometry is exactly same, but here 20 kilonewton is applied to the right, and to the left 10 only. So we have AY, we have BY, of course we have AY, we have BY. But this AY and this AY is totally different because applied loading condition is different. So in this case, the distance is 1 and 3, and this is 3 and 1. And can you try to get the answer for this AY? So you can try it, but I think I can skip it here. So once you get this answer, AY should be 7.5. I think I don't need to explain this here. It's not difficult. And this is 2.5 kilonewton. Don't forget the unit is pretty much important for us. And in this case, the AY should be 5 and BY is 15 kilonewton. So there is two different methods. Do you remember how to solve it? Two ways. You can use the section method using the statics. The other way is graphical method. So of course graphical method is pretty much easier. So I would suggest you to apply the section method, because in this case based on the applied load, in the case of section method, please keep in mind that if you want to adopt the section method, you should cut it here first and here. You need to split into two different range, about this range 1 and the other range 1, and in this case cut it here and there, so that you can get two different moment to complete the total moment condition. So anyhow, in here I'd like to adopt the graphical method, because this is the point load condition, so it might be easier. So the shear force diagram first, we have AY is 7.5 here, and till here 1 meter we don't have any force applied to the beam, and the 10 kilonewton is applied to downward, meaning that this should be negative 2.5. And let's move on to the right till the end, and at point B we have 2.5 upward. So this is the shear force diagram, and in this case if you try to plot it, then 5 is here, move to the right, and 20 down, so this should be negative 15, and move to the right again till the end we have 15. So this is the shear force diagram. So how to plot the bending moment diagram? Moment, because we know the area here, the total area, this one is 1 times 7.5, meaning that here the value should be 7.5, and this should be the straight line to upward linearly increased, and this is also 7.5 and 1, so 7.5 down like that. You know what I'm saying? And in this case you can plot this is moment X, So you can plot the bending moment diagram. In this case, this is 3 and 5, so 3 times 5, that is 15. So here the value should be 15 kilonewton meter, and down, you know what I'm saying? Sorry, it should be like that. So from the understanding of the principal superposition, we know that we can add those two, the moment 1x and moment 2x, so that the shape will be like let's see the final answer, like that. We have obtained the moment x, moment 1 and moment 2. So my suggestion is we need to split into 3 areas, like here this is range 1 and the other one is 2 and 3, and this will be 1, here is 2 and 3, so that we can add one by one, so that we could be able to the mx values, you know what I'm saying. But of course, if you use the graphical method, it will be much clearer, like here. So how to get that? This is your homework. So in this case, you can establish your free body diagram. You have AY, and this is V and M, and there is no force applied because we cut it here before 10 kilonewton met. So this is left hand side, and the right hand side here, there should be AY applied, and we cut it here so that V and moment, but we have 10 kilonewton at 1 meter. So this will be like this part, and this part will be like that, so that you can get the moment functions. And this is also same, like that way you can get it. So let's move on, and you can see here the solution. In here, the reading assignment, they try to make a general solution, so don't be confused on that. If you are confused, you can put it the exact number as well. So they split into 2 different areas, like range A, 0 to A and A to L here. Apply the loads 10 kilonewton, find the reactions, establish the shear and the bending moment diagram using the equation of equilibrium, so that finally you could be able to see here the maximum bending moment is occurred at here, that is 3 meter. You know what I'm saying? The value, you can, I think, easily get this 17.5, and I would say that the graphical method is much more easier, but please try and be practiced on the sectional method. So this is another example, as you can see here. So this is another example of how we're gonna apply this principle of superposition for this condition. So they have applied here, please look at this one. This is the original condition, fixed boundary condition, but they have applied the 2 different load types. The first one is point load P, and secondly, they have applied the distributed load. We call the UDL, uniformly distributed load. These could be split into 2. How? So boundary condition is exactly same. Distributed load Q is here, but at the center the point load is also applied here. So this is quite interesting for us how to deal with these questions. So I think you might be easily understand what I'm talking about. This is another case, prop beam. We learned that this is the indeterminate structures, and statistically indeterminate to the first degree. You can remind reading assignment 18 we have covered before, but what I want to talk is here, think about it, this could also be applicable for the boundary conditions. What I mean is, this is the propped cantilever. Left hand side you can see that this is fixed conditions, and the right hand side this is the roller. But they have changed the boundary condition, like here simply supported, this is pin and this is roller. What I mean is, they have changed the boundary condition fixed to the pin condition, but here you can think about, in this case, fixed condition AX, AY, and the moment should be applied. Of course, MA will be applied, and we know that AX is equal to 0 because there is no force applied to the x-axis. So we have moment A, isn't it? So they changed the boundary condition to the pin. So we have AY here, and the moment A is directly applied to this condition, and they would say that this is the same condition like this. So this is kind of assumption to solve it easily. So from the indeterminate structures to the determinate structures, so that it could be much easier to solve it. So this is the basic ideas. So think about it. So in this case, from here, so they split into two again, like simply supported beam, that is the same, but applied load moment 1 here, and in this case they have applied the uniformly distributed load Q and then add up those two. So decomposition of the load, and think about it, right? So once you try to get this answer, you could understand that from here simply supported beam, we have covered this one in the reading assignment 17 if I'm not mistaken, so that we could be able to get the moment distribution like this. And if you apply the moment A at point A, then the moment distribution should be like this. So add 1 and 2 so that you can get this one. This will be the final answer. Right? So this is the practice, and they are talking about uniformly increasing distributed load conditions. Like here, from the beginning I have discussed about the outer side shell of the ship's hull, and then we discussed about the P1 and P2, something like that. So this is exactly same, but in here, if you see example number 2, the expression is a little bit tricky, but make it simple. So as you see here, this is the deck, bulkhead stiffener, and the bottom floor. Anyhow, the height is the 5 meter here. As you can see here, this is the height, and we have additional height 0.6 meter. And once you read this, the water height of 0.6 above the deck, this is clear, and calculate the maximum bending moment. We want to know maximum bending moment for our design on the stiffened plate. If the spacing of the bulkhead stiffener, that is 550 millimeter. So basically I would recommend you to make it simpler like this. So simply supported boundary condition and applied load condition will be like this. You know what I'm saying? So I just put it this part here, like here. So this point is located here, this point is over there, deck and bottom, and of course this is 5 meter. And one more thing is we have 0.6 additional, so I will change the color. That should be considered as like that. This should be 0.6 meter, so it will be like that shape. You know what I'm saying? So that once you see these the simply supported beam and distributed load condition, it might be much easier, but my point is, don't be confused on these kind of new graphical expressions. All right, so anyhow, we have this one, and good thing is we have the function for the distributed load. And basically there are, I think you can try 2 different ways, not exactly different, but in here the reading assignment, it is much more clear, but I don't force you to follow these solutions. So from here they discussed about the Q is actually given from the questions. So how to define it? What we know is P, lateral pressure, that is low GH, and what we know is low still water, that is 1025 kilogram meter square. So anyhow, we want to know about the pressure level, right? So that is expressed by the Q in this example. So what we know is Q, this is same as low G, and what is the height? That is 0.6 plus 5. Oh, sorry, this should be considered as this, right? And we need to multiply A something that was 550 millimeter. Please don't forget, right? So based on this, you can see here we can understand what that is, and this express the apply the lateral pressure. You know what I'm saying? So after that, look at the unit. If you don't understand this unit and Q, because lateral pressure P is low GH, right? And if you think about force, that is low G and volume. So if you multiply area here, that will be converted to low GV. But in here, this is distributed load, meaning that, for example, the Newton per length meter or Newton per millimeter. So what we need is this unit, so that we need to multiply from here lateral pressure given equations times length 0.55 or 550 millimeter is needed. That's why from the beginning they have provided these informations, so don't be confused. So anyhow, we have this information. This is apply the load Q, so we should remember this one. And here, what's that? So they want to calculate the moment equilibrium about B, so that this one, we don't know the centroid for this, but what we know is Q will be applied at here, and we just assume that this will be the length applied and centroid location. So once you see further, they have tried to establish the free body diagram like here. So apply the moment. From here we should be able to get the reactions. So basically, let's see this one again. So 5 times, because the length is 5 meter, and this is the reactions. I think AY might be better expression. So 5 AY and integration, because what we need is the total force applied, that is same as the area. You know what I'm saying? Area is same as integration of this function, so that they have applied the integration 0 to 5 and the function Q, and 5 minus this one and integration, so that you should be able to get the exact number of the reaction force that is exactly same as this one. Alright, so after that we will cut the section here, for example around here or there, it doesn't matter because we will set X around here. So that is here. So reaction is obtained here, and this is X, and this is positive shear and positive moment. Of course this is exactly same function, and this is the length. So how to get this out? So moment, we will calculate moment equilibrium at here. So what we need is apply the reaction times the X here, and integration of this total area, right, times the distance is actually, for example, centroid is, for example, here. Then what we need is we need to measure the length. So that should be x minus this one. This is here, so that we could be able to get moment like that. You know what I'm saying? So that we can get this function later on, and the following steps are exactly similar. So once we get this one, then think about it. Like, we now have the moment function, and how to get that. Once we integrate it, this is same as EI, and then integrate it so that we can get this one. That is right, same as, what was that? The slope, right? So the maximum bending moment differentiating M, and with respect to the equation. Okay, so in here this is the integration way, and one more integration so that we can get deflection, but what they need is the maximum bending moment only. So in this case they differentiate it so that we will move this way. So mx differentiated so that there will be the shear force, right? So shear force, for example, the simply supported beam conditions, if the shear force is 0, that means the maximum bending moment is occurred. So this point, the physical meaning of the differentiating M with respect to x and equal to 0, this means that we want to get shear force equal to 0. That is the maximum bending moment position. So basically, we naval architect, marine engineers, we should be carefully think about the shear. The sign convention is, a sign is changing from the positive to the negative or negative to the positive, because that means maximum bending moment is applied at that point. So that using this relationship, we can get this equation, substitute x equal to 0, so that you can simplify it. Once you solve this one, then the answer will be like 2.82 meter roughly. And one more thing is the maximum bending moment. Just substitute these 2.82 to the original bending moment equation mx, so that you can get this number. At the same time, what I want to suggest you to do is, from the beginning, establish your own free body diagram like this, P1 and P2, and this will be AY, this will be BY. And what I mean is, you don't need to use the function, but you can simply find this number. You know what I'm saying? Because we have this is 5 meter, this is 0.6 meter, and this is log h, so that P is log h, so that you can get this number. You know what I'm saying? This should be log h is 0.6, this is log 0.6 plus this one 5, so that you should be able to get these numbers from the beginning and then split it into two. Like, this is applied to the simply supported beam, like P1 plus this is P2 minus P1, so that once you get this one and this one, you can get mx1, m2x, and later you can add up total. So let's try this one, and then my calculation is, give me a second, you should be able to get, if you follow my suggestion, you should be able to get the moment, the total x, that is nearly negative 9173 x square right? So using this, you could be able to get similar number like this, as well as x, the position that was nearly 2.82 meter, right? It's up to you. You can choose this integration way by setting the lateral pressure function, or you can split into two using the principles of the superpositions. So I would recommend you to try both method and understand it clearly. So that's all for today, and thanks very much. Bye bye.